So like Doug said, my name is Julie Hendricks, and I'm here today to talk to you guys about proper sampling and particle size analysis for animal feed grinding. Sorry. So a little bit about me. I'm originally from Diller, Nebraska, which is about 7 miles from the Kansas-Nebraska border. And I'm an alumni of Kansas State University 2 times, which is where I did my thesis about particle size and sieving methodology, which is a great read for all that are interested. I have about 10 years of industry experience and then also conducting research. Married to my husband, Justin, and then also some interest I have all things Kansas State, as well as cows, antiques, and cycling. And for those of you interested, yes, I live in Iowa, and no, I have not ridden RAGBRAI. So an overview of what I'll be talking about. So first I'll start off with obtaining and splitting the samples, and then moving on to defining what particle size analysis is, and then providing the procedure as well as some comparisons, common problems, and answers to common questions. And we'll end with a summary. And then also at the end, we'll have time for any remaining questions you may have. So first, we want to start off with obtaining samples. And for this, we want to obtain a representative sample that is the same as our finished product. And so with this, we want it to have the whole range of particles from the smallest to the largest particles in that finished product. And then after we obtain the sample, we will split and divide it and then do our analysis from there. And so with both of these pictures, so on the left, I have a diagram of a hammer mill system, and then on the right, a picture of one of our roller mills. And so the red arrows indicate the product flow through each piece of grinding equipment, and then the blue circles indicate possible or potential sampling locations. And so sampling is similar to real estate. It's all about location, location, location. And so we want to also, with this, we want to make sure that we're obtaining that sample after the fines are reintroduced. And this comes into play on a system where we have an air system, so such as a hammer mill, or potentially some of you have an air system on your roller mills as well. And so on the left picture with the hammer mill, we want to make sure that we're getting that sample after. This system has an airlock, and so that's also where that air system is not going to affect our sample. So likely there is a transition to a bucket elevator or to another piece of equipment at that blue circle on the hammer mill. So, and then on the roller mill, our roller mills have slides or gates that can be opened and closed to obtain a sample underneath each set of our rolls. And so on a roller mill, we have the opportunity to obtain a sample on the left, right, and middle length of those rolls. And then that also allows us to make sure that the rolls are being fed evenly across the length of those rolls, as well as making sure that that grind size is uniform across the length of those rolls. And if it's not, we're able to correct problems from there. So after we've obtained that representative sample, that's where we're going to split and divide it, and then from there do the analysis. And so we want to split and divide that representative sample down to approximately 100 grams. And it's important that we don't scoop this material off of the top of the pile or off of the top of our sample bucket. This is because we do experience particle segregation, where those fines tend to settle to the bottom and the overs or the larger material rise to the top. And so there's two ways we can do this. The top two pictures are of a riffle divider, and this is the most common and simplest for most applications. This is used for animal feed and feed ingredients. And it does this by having chutes that discharge in opposite directions. The other method is quartering, which this can also be used if you do not have a riffle divider, but it is used for high roughage feed that contains hay or grass. And we do this by spreading the sample out evenly onto a piece of paper or plastic and then dividing from there. And so then, like I said, we take that split and divided sample that is approximately 100 grams and do particle size analysis. So what is particle size analysis? There's a standard with the ANSI ASAE S319.4. That's the current version. But this is designed for animal feed and feed ingredients. And within this, the amount of sample in the sieves is described. So two definitions that are described within that standard, and also definitions that I'll be referring to throughout this presentation. First is the geometric mean diameter, which is given the units of microns. This is often referred to as the average particle size. And then the geometric standard deviation, which is the variation around that particle size. So the higher the standard deviation indicates the more variation, and then this is usually less preferred, whereas the lower this number, the less variation, and this is more preferred. So keep in mind that the lower the standard deviation, it may be preferred, but it's not the most accurate. So with accurate quality control in mind, we want to note that each product and process varies, but we still want to obtain the most accurate standard deviation based on that particle size. And so with accurate results, we can compare the results. And so the procedure for particle size analysis I have listed here. We want to start with each sieve, making sure that it's cleaned, as well as the sieve agitators in their proper arrangement, which I'll talk more about what sieve agitators are, as well as a recommended arrangement for them later on in the presentation. So, and then we take our representative sample, and that we split and divided to approximately 100 plus or minus 5 grams. And we add and mix in 0.5 grams of sieving agent and place this mixture on the top sieve of the sieve stack and into the shaker machine for 10 minutes. And afterwards, we weigh the material on each sieve and then calculate our results. And after every analysis, we should be cleaning each sieve with either a brush or compressed air, and then putting the sieve agitators back in their proper arrangement so that the sieve stack is ready to go for the next time. So for the equipment that we use for particle size analysis, the shaker machine is a Rotap machine. And you can see the picture on the right side with the Rotap machine with a sieve stack placed inside of it. So the Rotap machine uses a bar on the top to tap it while the sieve stack itself rotates in a circular motion. And so that red arrow indicates the direction that those particles will move throughout the sieve stack. And so that screen size opening decreases from the top to the bottom. So that means that that sample that we placed on the top of the sieve stack, the larger particles will stay towards the top, and then the finer particles will continue moving throughout the sieve stack until that opening is smaller than the individual particle. And so the picture on the left, you can see that we have some rocks that were analyzed, and you can see the amount of sample and the size of that sample that was on each sieve. Sorry, excuse me. And so I talked about sieve agitators and sieving agent and the procedure. Sieve agitators are brushes and balls, and they're a wear item, so they need replaced as needed. But we want to make sure that we're using the same type and size as much as possible throughout the sieve stack. And there's an example of one ball and one brush in the lower right-hand corner on a sieve. But the purpose of sieve agitators is to, one, assist moving the particles throughout the sieves without grinding them any further. And then also to prevent buildup and blinding on the sieves. And blinding is where material will plug or clog the sieve, preventing other particles from passing through. The two bottles on the bottom are examples of sieving agent, and this is a silica powder, and so its main purpose is to, one, prevent blinding while also preventing agglomeration or those particles binding to each other. And it also assists those fine particles, mainly equal or less than to the 420 microns or the US number 40 sieve, moving throughout the sieves. And so, like with the agitators, we want to make sure that we're using the same type and size of those sieve agitators as much as possible. We also want to make sure that the sieve material is the same as much as possible throughout. And so there's two types of sieve materials. The first one is stainless steel, and it tends to be more expensive, but it tends to also have a longer wear life because it tends to not corrode. Whereas the other material of brass tends to be cheaper, but certain materials tend to bind to brass and it's more prone to corrosion. So it's whatever works best for your process and your facility. And then as far as the sieve screens, so each sieve will have a nameplate on it, and I have an example of a nameplate here on the picture on the left. And on that nameplate will be the US sieve number, which indicates the number of wires per inch. Some of you may also have the Tyler sieves, which the Tyler sieve number indicates the number of openings per inch. For this presentation, I'll be referring to the US sieve number, but as you'll see in the next slide, you can convert between the two. And then also the sieve opening is listed on the nameplate in millimeters and in inches. And so the picture on the right is an example of 3 different sieves with their respective openings. And so you can see on the number 6 screen that sieve opening is larger. And then as we increase the US sieve number, that opening decreases. And so like I alluded to, so we have the US sieve number, and then I also have the coordinating Tyler sieve number listed. And so as I alluded to on the previous slide, the US sieve number, as it increases, as we move from top to bottom in the sieve stack, that sieve opening decreases, and because we have less openings per inch or less wires per inch. And then also we have the sieve agitator arrangement listed, and this is a recommendation based on Kansas State University. And so it varies the number of brushes and balls on each sieve. And so some of you may use a different number of sieves. And so what we did here is that we ground to different target micron sizes and used the same sample for these 3 tests, only changing the number of sieves within that sieve stack. And so you'll notice that and moving on to, here's the last target micron size. So you'll notice that with the increased number of sieves in that sieve stack, we got a higher standard deviation. And this is because those particles were separated out more throughout the sieve stack, which provided us a more accurate result. And so continuing on with our goal of obtaining the most accurate standard deviation based on that particle size, we compared using sieve agitators and sieving agent in different combinations. And so with this sample, once again, it was the same sample, except it was divided and analyzed 3 different ways. And so when we used in the black box, you'll notice that when we use sieve agitators and sieving agent together, we obtain the lowest particle size and the highest standard deviation, thus giving us the most accurate result. And then also when we compare our grinding method with a hammer mill versus a roller mill, we did a webinar on this previously to further explain why we typically see these results with a hammer mill and a roller mill, but this is largely to the method of grinding, where a hammer mill will have more variation in that particle size, and a roller mill will typically have a more uniform grind, which is also shown in that standard deviation. Which, if you have more questions about hammer mills and roller mills, please refer to that webinar. And so also 2 common problems that we see that lead to inaccurate results. So first is contributed to sampling error. And so we see the effect of taking shortcuts, whether it's not obtaining that sample from the same location each time, or not consistently dividing and splitting that sample the same way each time, we get inaccurate results. And so to demonstrate this, we analyze the same sample, just splitting and dividing it differently. And so the first column, we split and divided the sample until we got to exactly 100 grams. And then the middle column, we split and divided the sample until we got to about 103 grams, and then removed 3 grams from the sample on the scale to get to exactly 100 grams. And then the last, we scooped off the top of the pile and then just poured onto the scale until we got to 100 grams. And so you can see the variation in results that we obtained with doing that. And so the middle column where we removed the excess sample, we want to avoid doing that, especially because we're doing more harm than good. And this calculation, it's percentage based, so we're better off to leave that 3 grams on there rather than to get to exactly 100 grams. The other common problem we see is with screens blinding over. And so once again, this is an example where you can see on the right picture where that screen's blinded over with the material plugging or clogging the sieves, and that prevented other particles from passing through. Whereas on the left screen picture is an example of a clean screen that's not blinded over. And so we see the blinding most commonly as that grind gets finer. And this is contributed to not using sieve agitators or sieving agent, as well as product buildup. And we see product buildup especially on high fat products. And so to demonstrate the effects that sieve agitators have on the results, we did one sample and split and divided it and ran the sample with sieve agitators and without sieve agitators. And so when we use sieve agitators, we obtain a lower particle size and a higher standard deviation. And this is mainly contributed to that the material on the number 70 sieve moving to a more proper or designated sieve throughout that sieve stack. And then we did the same process using sieving agent. So this is also the same sample, just split and divided, and ran the analysis, one with sieving agent and the other without sieving agent. And so you'll notice the same effect where we obtained a lower particle size and a higher standard deviation when sieving agent was used. And this also shows us that in order to get accurate results, we need to be using sieving agent, because otherwise we're not getting accurate results and therefore we're wasting our time. And so moving on to common questions. This question, how often should I clean my sieves? It's a question that we don't often receive, but we probably should. But the answer is we should clean them as often as reasonably possible. And so after each analysis, we should be cleaning with a brush or compressed air. We just want to make sure that we're not damaging or tearing those screens. And then also, if we experience screen blinding or product buildup, that's where we would use washing with soap or water or the equivalent of a degreaser. And once again, we experience the product buildup, especially on those formulas or ingredients that are high in fats and oils. And so to demonstrate this, we ran the same sample 5 times consecutively. And after running sample number 4 and before running sample 5, we cleaned those sieves. And so you'll notice that the particle size steadily increased after every sample and the standard deviation decreased. And then after we cleaned the sieves and before doing sample number 5, those results returned back to being similar to sample number 1. Other common questions we receive, how often should I analyze a sample? This depends on your process as well as your quality standards. But keep in mind that the more frequent you analyze a sample, you have more control over your process, and then therefore you're able to react to any changes in your process quicker. How often should, and then why are my results different than my third-party results? This is due to a difference in analysis methods. So you just want to make sure that you're comparing apples to apples so that you're both using the same sieve agitator arrangement, the same number of sieves within that sieve stack, as well as sieving agent. And then the last one, so should I be using sieving agent? Yes, most definitely, as we showed earlier, because sieving agent, we're getting a higher standard deviation and therefore a more accurate result, because otherwise, if we're not using sieving agent, we're not getting accurate results, and therefore we can't compare them and it's a waste of time. So in summary, the purpose of particle size analysis, we want to accurately measure that ground material, and to do that we need to get the most accurate standard deviation based on a particle size. So this starts with obtaining accurate samples and splitting and sampling them correctly. And then keep in mind that particle size analysis, it's not perfect and it varies based on the product and the process. So that's why consistency is key to make sure and making sure that you're using the same method and arrangement, and then also your technicians are obtaining and splitting those samples the same way each time. And with that, I'd just like to thank you for your time, and I will take any questions. And also, please feel free to reach out to me after this webinar for any further questions or problems you may have. Thank you.
Hey, thanks, Julie. A couple quick questions here already. I've got a couple based on the same topic, and that's sieving agent. Question is basically kind of, what's the importance of it, which you touched on already in your webinar, but the next one is, the follow-up to it is, if it's not possible to use sieving agent, is there a correction factor that can be considered, or how do you take into account if you are not able to use it?
Well, as far as I know, there is no correction factor for not using sieving agent versus using sieving agent. But how do you take it into account? I do not know of a simple way, unless you do, Doug.
I mean, would you just kind of more or less look at it from, you're probably, your results are showing a coarser number than what you're actually grinding to. But as far as, if you had to shoot from the hip and pick a number, if you're not using sieving agent as compared to it, is there a rough micron size you say, hey, assume 50 microns less or something? I get there's a lot of variables that go in there, but is there some rule of thumb at all? If the answer is no, that's fine.
There's not one as far as I know. And with doing the research, that varied based on the grind size, and it varied based on that grinding method. So there wasn't any consistent number that we determined.
So hard and fast rule, I guess, basically is just assume that if you're not using sieving agent, your numbers are coarser than what you're actually grinding to.
Yeah.
Okay. There's another question that's, what can I do to help reduce my standard deviation within the mill?
There's a lot of factors that can go into this. But as far as with the hammer mill, this also depends on your grinding method. So if you're grinding with a hammer mill versus a roller mill, the hammer mill will typically have a higher standard deviation just based on that grinding action. But as far as getting a more uniform grind, this is where you want to make sure that if you're using a roller mill, that your roll gap settings are consistent so that each set of rolls is doing the same amount of work and not producing fines within that process. This is also where you can look at your product moisture. So if your product moisture is low, so if you, for example, if you're using old crop corn versus new crop corn, the lower moisture product will tend to break more, thus producing more fines and increasing your standard deviation than if you have a higher moisture. But there are consequences to using a higher moisture product as well. So.
Well put. The only thing I would add to that actually is we have done webinars that actually go over some of those exact same things. I was actually the one that put them on. We can share those links with you if you're interested as well. That appears to be the majority of the questions we're going over. I'll give it a, nope. The one just came in. Julie, you can go to this, I guess, or maybe you can decide if you want to reach out afterwards on this, but the question is, what is the theoretical equation of calculating mean particle size?
Oh boy. So We use a spreadsheet, as well as many other people also use a spreadsheet, where we use a series of logarithms and natural logs, and it's all into that spreadsheet, and it's all percentage based. And so we can share a spreadsheet with you that would better explain in more detail those equations.
Julie, isn't it essentially you're kind of looking at the whole size of the screen above it and lower than it, and kind of taking an average of the material on there with the whole size that's above and below it, and using, that's how you're using your logarithmic function?
Yeah, which is also why the more sieves that we use within that sieve stack, it decreases that difference between the sieve opening from one sieve to another, which is why it also increases our standard deviation, because we're separating that out more.
Perfect. That appeared to answer the question too.
Thank you.
All right, well, I think that's it for now. Like I said, Julie just mentioned, if you do have any additional questions, you're always welcome to reach out to us or her directly, and we'll be happy to help you guys out.
Thank you.